We live in the heart of a great mystery. A mystery called the universe. We can measure it, analyze it, observe it, and even explore it. But what is the universe? How did it begin? Why did it begin? And how might it end? Some people reject the idea that it started with a Big Bang. Cosmologists generally accept the theory, but while they can explain how, they have no idea why. This is the theory of the Big Bang. From a single cataclysmic explosion, everything springs. From a speck smaller than an atom emerge matter, space, and time. It's blindingly hot. In the first microsecond, the universe expands to the size of a galaxy. It's a particle soup, growing bigger and bigger. It's so hot, energy spontaneously generates matter and antimatter. They annihilate each other and start again. Matter wins by 1 part in a billion. Matter is to dominate our universe. Protons, neutrons, electrons. The universe is now 1 second old. It's opaque. We can't see a thing. But scientists work it out. This expanding maelstrom seethes with subatomic particles. Atoms are about to form. At 3 minutes from the Big Bang, they create the first chemical elements: hydrogen, helium, and a trace of lithium. For 300,000 years, the cosmos is a fog. But as it expands, temperatures drop. Our universe becomes transparent. For the first time, light and other radiation speed across space. A telescope can't show us the early universe, but a particle accelerator can. This is an atom smasher. Electrified particles are crashed into each other at approaching the speed of light. For a split second, we're in the earliest universe. The collisions reproduce, fleetingly, the subatomic particles that abounded immediately after the Big Bang. The veil is lifting on the opaque universe. In 1965, Americans Robert Wilson and Arno Penzias detect the first radiation of the visible universe. The horn behind them picks up a microwave hiss from every direction, an echo of the Big Bang at -270 degrees Celsius. As the universe has cooled, that signal, originally in ultraviolet, has shifted to microwave. It's called cosmic background radiation. This is COBE, the Cosmic Background Explorer. It makes sense of the microwave hiss. Like a supersensitive thermometer, COBE takes the temperature of the universe, first removing the solar system, then the Milky Way. What's left is an ancient temperature chart. From the first radiation of the visible universe, evidence that a primitive structure has emerged. That structure takes 1 billion years to develop. Ever expanding, galaxies in clusters, clusters on strands, the voids between growing wider and wider. Here, mutual gravitational attraction draws groups of galaxies into clusters and clusters into superclusters. How galaxies form is a puzzle. We know how a supercluster like this evolves. But its collisions and mergers make it hard to unravel the earlier history of individual galaxies. Computer simulation confirms that the evolution of a supercluster is a violent affair. Some galaxies spin right out of the system. Gravity conducts a chaotic dance. It may last for billions of years. Young galaxies in the very early universe appear small and irregular, the product possibly of the repeated merger of smaller clumps. Those infant galaxies bear little resemblance to a mature spiral like this. Current thinking is that galaxies grow from smaller aggregations of matter in merger after merger. Subsequent development like this is better understood. Galactic interaction is the norm. Often it's cannibalism, big galaxies ingesting smaller ones. It continues to the present day. But where are we today? How old is the universe? If it's expanding relatively slowly, we can deduce that the Big Bang happened some 15 billion years ago. If it's expanding rapidly, then the universe is younger, between 10 and 13 billion years old. Winding back to the Big Bang is one way to learn more. Another way of aging the universe is to look at stars hovering outside the plane of our galaxy. Such stars form groups of up to 1 million. Called globular clusters, they contain the most ancient stars in the universe. By analyzing their light, the age of these stars is initially set at up to 15 billion years. But the first wind-back results put the age of the universe at only 11 billion. These stars can't be older than the universe. The satellite Hipparchus helps resolve the issue. Its mission is to measure the distance of thousands of stars with unprecedented accuracy. Hipparchus employs parallax. It measures the shift of a foreground star against a more distant star. It does so from opposite positions in Earth's orbit of the Sun. The accuracy of Hipparchus is like measuring a golf ball on the Empire State Building from the other side of the world. Hipparchus proves that certain stars are 10% further away than we thought, making the universe between 13 and 15 billion years old. Hipparchus finds that globular clusters are also further away, making their stars younger, at between 12 and 13 billion years old. The older the universe, the slower it expands. So, could it stop and reverse? Maybe. But one theory suggests the expansion of the universe will go on and on till, like a firework, momentum runs out. The universe will be dispersed, bleak, and lonely. The theory of the Big Crunch is more dramatic. When expansion is exhausted, the universe teeters and travels backwards. It could only happen if there's enough matter in the universe. Matter creates gravity. Only gravity can orchestrate such a terminal crunch. There may be enough matter for a big crunch, for 90% of the universe is thought to be invisible. Far from city lights and with just a whisper of cloud, the Milky Way straddles the sky. This delicate band of light is our home in the cosmos. For when we observe the Milky Way, we're looking sideways at a disk of stars. That disk is our galaxy, our island universe. From above, the Milky Way is a spiral, a family of some 150 billion stars. We belong to that family. Our Sun is one of these stars. It lies 2/3 of the way from the galactic center. The Milky Way turns like a Catherine wheel, great arms spiraling outward. Within one of those arms, the Sun orbits the galactic center once every 225 million years. Like a city, the center shines brightest of all. Veiled in gas and dust, it seethes with energy. But our neighborhood is suburban, quiet stars leading ordinary lives. The Sun is no exception. It's yellow, average, and middle-aged. For an idea of scale, light from the Sun takes 8.5 minutes to reach Earth. Light from the nearest star takes 4.25 years to reach us. Astronomers call the distance 4.25 light years. The Milky Way is 100,000 light years across. From our position to the galactic center, it's 30,000 light years. The constellation of Orion rapidly loses shape as we hurtle through space. Stars that seem close together from Earth are really hundreds of light years apart. But in the vastness of our galaxy, we're still close to home. This group of young stars, called the Pleiades, is 380 light years away. Closer are the Hyades, older, dimmer stars, at 150 light years. And although from Earth it seems to be in the Hyades, this orange giant is less than half the distance. Aldebaran, over 100 times more luminous than the Sun. Sirius, the dog star, less than 9 light years, the brightest star in our night sky. Barnard's star, a red dwarf, 2,000 times dimmer than the Sun and on its way towards the Sun. As it sweeps by in 10,000 years' time, it'll be our closest galactic companion. But for the time being, the nearest is Alpha Centauri, a trio of stars just 4.25 light years away. To see where stars are born, we must first look at another galaxy. This is M83. Glowing pink in its spiral arms, regions of starbirth. In our galaxy, these are like nurseries. They're called emission nebulae, clouds of glowing hydrogen streaked with black dust. Stars fire up where material clumps. Lower left, a brilliant young star in its dusty cocoon. And here, white hot, groups of new stars. The black dust in this nebula is scattered far and wide, dispersed by the winds of fierce new stars. Stellar birth is violent. Blowing together, an array of energetic infants clears this gigantic bubble in a red nebula. Young stars blow a whole 12 light years across at the heart of the Rosette Nebula. The more massive the star, the shorter its life. Average stars, like our Sun, live long. Massive ones die young. Voraciously consuming their fuel, they become red supergiants, bulging to hundreds of times their original size. This one, Antares, is enveloped in a cloud of its own material, a reflection nebula. Antares is so big and diffuse that it leaks into space. A star like Antares, more massive than the Sun, swells as hydrogen runs out. It switches to helium and other elements, but equilibrium is lost and it grows. Radiation pushing out beats gravity pushing in, and that's its undoing. The red giant puffs into space. The core exposed, it collapses to become a white dwarf. And here's the real thing, a dwarf in a stellar smoke ring. Astronomers call it a planetary nebula. This one has wings, blown into the shape of a butterfly by ferocious winds. Another with more extended lobes, the legacy of a red giant. One of the most beautiful is from the demise of the giant that gave us the Helix Nebula. 300 light-years from Earth, the Helix is our nearest planetary nebula, the white dwarf at its center, visible in this actual picture. The white dwarf, lower right, leads a busier life. Its gravity draws material from a companion, but when the matter reaches a critical mass, it explodes into a nova. Both stars survive, and the process repeats. Bigger stars make bigger bangs. This red supergiant has 10 times the mass of the Sun. The Sun lives 10 billion years. This star, just 20 million. It's fast, furious, then finished. The explosion is a supernova. Here in the Crab Nebula, a supernova is observed from China in 1054. Its debris is the nebula. Within the Crab, a pulsar survives. Spinning 30 times a second, it's a super-dense relic collapsed from the original star. Around it, a disk of material and matter jetting from the poles. Trained on the Crab Nebula, the Hubble Space Telescope reveals more. Time-lapse shows shock waves from the pulsar, particles spinning from the disk at close to the speed of light, whipped into space by the whirling magnetic field. And here, matter from a polar jet hitting slower material in the Crab. The elegant tendrils of the Cygnus Loop, another supernova remnant. To exit in such glory, a star must have at least 8 times the mass of the Sun. Only superstars go supernova. With 100 times the mass of the Sun and venting great clouds of material, a pre-supernova symptom, this star, Eta Carini, may be the next to blow. And when it does, the remnant will collapse beyond the pulsar stage. It will be so dense, it'll form a black hole. Birth, life, and death in our galaxy. And there are far more galaxies in the universe than there are stars in the Milky Way. Australia is the starting point of this voyage into space. Travel is supposed to broaden the mind. This journey is to measure the cosmos, to set our position in the broadest context of all, the universe. We begin in Australia because it's good for observing the nearest galaxies. 2 mini-galaxies, called the Magellanic Clouds. The small cloud is to the center, the large at the right. In the large cloud in 1987, a supernova blows. In fact, this supergiant expired 160,000 years ago. It's taken that long for the light of the flash to reach us. Andromeda is our closest major galaxy, at over 2 million light-years. At 10 million light-years, the Silver Coin Galaxy, a spiral like Andromeda, and like our own galaxy, the Milky Way. We probably look like this. A spiral from above, the M83 galaxy, also at 10 million light-years. We're now at twice the distance. The light of this galaxy takes 20 million years to reach us. This one, 35 million years. And from the beautiful Sombrero galaxy, 40 million years. Vast distances, but all these spirals are relatively close to us. This galaxy, Virgo A, is different. It's shaped like a basketball, an elliptical galaxy, one of a cluster of up to 60 million light-years distant. The Virgo cluster is part of a supercluster of about 1,000 galaxies. Galaxies cluster because of mutual gravitational attraction. But how do we know this? How do we measure the cosmos, or even the distance to our galactic center? Our galaxy is one of 30 in a local group. That group is part of a cluster, and the cluster is part of a supercluster. Superclusters form strands across the universe. To help construct this model, astronomers use what they call standard candles. There's a standard candle in this galaxy, a pulsing star that brightens and fades as regular as clockwork. It's called a Cepheid variable, a star whose brightness varies as it expands and contracts. This one is big and bright and pulses slowly. But this Cepheid is smaller and dimmer and pulses faster. The speed of a Cepheid's pulse is directly related to its intrinsic brightness. So if we know the distance and true brightness of these nearby Cepheids, we can calculate the distance of remote Cepheids, Cepheids that appear fainter but beat with the same pulse. In this way, we know that the Andromeda galaxy lies at a distance of 2.2 million light-years. Cepheids in our own galaxy are compared to fainter Cepheids here in Andromeda. But ground-based telescopes detect Cepheids only out to 15 million light-years. It takes the Hubble Space Telescope to see them in this galaxy at 55 million light-years. And in this galaxy at 80 million light-years. To reach further, another sort of standard candle is needed. Astronomers call it Type 1 supernova. It occurs in a two-star binary system. A white dwarf, a star at the end of its life, swirls at the center of an accretion disk. It draws material from its partner. When the dwarf reaches the mass of 1.5 times our Sun, it explodes, a Type 1 supernova. The flash intensity is always the same. It's our new reference standard candle. From Cepheids, we know the distance of this galaxy. But because it also has Type 1 supernovae, that gives us the distance to our new standard candle. That candle, a Type 1 supernova, lets us measure up to 100 times deeper into space. But our journey has barely begun. In the 1920s, the American astronomer Edwin Hubble discovers our expanding universe, galaxies traveling outward in all directions. The evidence is in their light. As a galaxy speeds away, the lines of its spectrum move increasingly toward the red. The further and faster a galaxy recedes, the greater the shift into red. The measurement of red shift is the greatest tool in the sizing and shaping of the cosmos. It suggests that the distance to the furthest reaches of the universe is 15 billion light-years. Mapping the heavens in the early 1960s, astronomers identify points of intense radio noise. Through optical telescopes, the sources appear as ordinary stars. But they can't be, for red shift puts them at billions of light-years distant. They're not radio galaxies. This one, Centaurus A, is noisy but less energetic. Nor are they Seyfert galaxies, radio sources that have brilliant cores. Seyferts are 100 times less energetic than radio galaxies, and at least 10,000 times less than the new sources. But all three are fueled by supermassive black holes, voracious concentrations of gravity. The black holes in the new sources are gigantic, devouring the equivalent of up to 600 Earths a minute. For radio astronomers have discovered quasars. Quasars are superluminous. They're the most energetic objects in the universe, and among the oldest and the most distant, with enormous red shifts. Our sizing and shaping of the cosmos yields yet another great discovery: colliding galaxies. This is such a merger, the antennae galaxies. Simulated on computer, the two spirals don't really collide, but swing through each other like cosmic pendulums. Their gravitational interaction ejects two great tails, like the antennae of an insect. The merger triggers a starburst. New stars are born. The antennae are 63 million light-years away. At their center, a firestorm of starbirth. This collision is like a spanner in the works. The intruder galaxy has passed right through the larger one, disrupting its structure. Here's a real picture of the same effect. It's the Cartwheel galaxy, scrambled as one of the small galaxies on the right plowed through. In this collision, neither galaxy emerges. Instead, a supergalaxy is formed. In 10 billion years' time, that's possibly the fate of our own galaxy, when we collide with Andromeda. A supernova, the death of a giant. The entrails of a star up to 100 times the mass of the Sun splatter across space. But out of catastrophe comes regeneration. From the debris, new stars are born. They fire up in regions like this, clouds of gas and dust, nebulae enriched by the supernova. For the blast carries metals like iron and gold, heavy elements spawned only in the most massive stars. This is how a supernova seeds its offspring. In this birth, a cloud of debris collapses under its own gravity. It forms a disk. At the center, a star begins to shine. Around it, rings emerge, rings that resolve into planets. Our solar system evolves this way. Earth orbits comfortably in the blue habitable zone, where life is possible. A rain of comets brings us water. Lightning is possibly the catalyst for life. Our early atmosphere is thick with carbon dioxide. But Earth is a beneficiary of that supernova. We're rich in phosphorus and sulfur, elements essential to living cells. As those cells evolve into higher life forms, green plants breathe oxygen into the air. Earth becomes the perfect incubator for life, neither too hot nor too cold. We're at just the right distance from the sun. The same can't be said of Mars. It's a freeze-dried desert where, even on the warmest days, temperatures barely top zero. For Mars lies just beyond the habitable zone. Yet less than a century ago, some astronomers believed in Martians, a civilization that dug a network of canals to carry water from the poles. Alas, these imaginary channels never irrigated a green planet. But Mars may once have had oceans, and just possibly microbial life. The oceans disappeared, it's thought, because Mars is so small. Weak gravity allowed the atmosphere to leak into space. Stripped of its warming effect, the red planet froze. Today, the polar caps are a visible remnant. But many scientists believe vast reservoirs of water lie frozen beneath the surface. And who knows, microbes may survive there, or at least a fossil or two. But if we find new life in the solar system, it's most likely to be here. This is the extraordinary surface of Europa, a satellite of Jupiter. A little smaller than our moon, Europa is totally covered in frozen water. It may be several kilometers thick. This pack ice on Earth looks remarkably similar, and beneath it lies an ocean. If Europa's the same, great seas may wash under the icy crust, and they could be warm, heated by volcanic activity. As in oceans on Earth, hot vents may support primitive life, organisms that feed on chemical rather than solar energy. Europa must be explored. Onward and outward. We're now so far from the heat of the sun that no life could possibly exist. We've reached Saturn, where the temperature of its cloud tops is minus 180 degrees Celsius. But the gas giant isn't our quest. We're headed for Saturn's largest moon, Titan. Titan is a laboratory for the origin of life. With a surface temperature of minus 200, it's an unlikely place. But Titan's cloudy atmosphere has lots of hydrocarbons. They react with ultraviolet light from the sun. Photochemical reactions produce organic molecules. Such carbon-based compounds are the first stage in the next generation of life. But it is too cold on Titan to pass to the next stage. Titan is like Earth in deep freeze. The atmosphere, like ours, is rich in nitrogen. It contains water molecules, here in blue, a legacy of the comets. The ingredients of early Earth are present. To come alive, all they need is heat. They'll get it 5 billion years hence, when the sun swells into a blazing red giant. Since 1983, this dish has listened out for extraterrestrials beyond the solar system. We've sent messages with the Pioneer and Voyager spacecraft. But from the stars, there's been not a peep. Nevertheless, evidence mounts that other stars have planets. Among them surely must be an Earth-like world. Such planet-forming stars are born in nebulae like this, clouds of gas and dust that pervade our galaxy. The excitement for astronomers is that these clouds contain the building blocks of life. They have water and organic molecules. As a star forms at the heart of a collapsing cloud, so the disk that emerges spins its center clear of debris. That debris makes planets. Here's a real star with a protoplanetary disk. And another, both pictured by the Hubble Space Telescope. This animation is of the star Beta Pictoris. In the clear center of its disk, a planet orbits. We may not be able to see a planet, but we know it's there because its gravity tugs on the star. The star wobbles. Astronomers detect the wobble by means of the Doppler shift. The star is blue as it moves towards us, red as it goes away. This Hubble image is a puzzle. It shows a pair of stars that have apparently ejected a planet. A trail leads us to it. Is this the first direct view of a planet outside our solar system? This one isn't a planet. It's a brown dwarf, with up to 50 times the mass of Jupiter, but too small to be a star. So far, of stars discovered to have a planet, none could support life. This planet has too close an orbit. The problem with this one is too distant an orbit. But when we do find an Earth-like planet, it's bound to be more mysterious than we have ever guessed. No one has ever seen a black hole, for nothing, not even light, escapes such gravity. Like black holes, 90% of the matter in the universe is invisible. Astronomers call it dark matter. This hidden mass is undetectable at any wavelength, from gamma rays to radio. With 9/10 of the picture obscured, our ideas of the universe could be quite wrong. Dark matter may be largely responsible for the development and structure of the universe. The problem is, most of that structure is invisible. For all we know, the cosmos is made of monsters. two stars orbit a common center of mass. They have a mutual gravitational attraction. We don't see the gravity, but we see its effects. The gravity of dark matter affects the rotation of this galaxy. Its spin is measured by the colors of the Doppler effect. Results show that outer parts of the galaxy spin much faster than its visible matter justifies. The cause is dark matter. Probably a hidden halo of up to 10 times the visible mass accelerates the galaxy. But dark matter shouldn't be confused with the dark clouds that pepper this galaxy. They're just visible dust. The matter we seek tugs invisibly on these stars. And it hints at a presence in these clusters of galaxies. Their interactions suggest up to 100 times more matter than we see. But what is dark matter? Is it dead stars, or failed stars, or black holes? Or is it exotic subatomic particles? This is the visible cosmos as we know it. The nature of dark matter and its part in shaping our universe remain two of the greatest mysteries in cosmology. A superstar draws matter from its smaller partner. The big star dies in a supernova, but the partner survives, still orbiting, still losing matter. For the superstar is now a black hole. In the real cosmos, we'd see the surviving star apparently orbiting an empty space. It's a clue used by astronomers to detect black holes. This is another. Although invisible itself, a black hole distorts light and space at its rim. Approach too close and you're spaghettified. A black hole is a collapsed star of such density, such gravity, that from within the rim, nothing escapes. To form a black hole, the core of the exploded star must be at least 3 times the mass of the Sun. But imagine Earth as a black hole. The mass of our planet is compressed to just 8 millimeters. It is so dense that light cannot escape, and nothing travels faster than light. But light can be bent, and it helps us find dark matter. Here, light from a distant quasar travels to Earth. Put a big object in the way, and our picture distorts. The object might be a galaxy with lots of dark matter and enormous gravitational pull. That gravity creates a crazy lens. It tugs on the light of the quasar, bending and multiplying its image. The picture we get on Earth is 4 images of the quasar with the lensing galaxy at the center. The degree of light bending reveals the amount of dark matter in the galaxy. When the lensing object is less symmetrical, it smears light. The blue arcs are far-off galaxies distorted by the cluster in the foreground. But the principle is the same. Gravitational lensing enables scientists to weigh dark matter. In the Milky Way, shrouded by the stars that crowd our galactic center, is a ring of gas. It has the mass of 30,000 suns. To many astronomers, such a swirl is evidence of only one thing: the pull of a massive black hole. A throat at our galactic center that has swallowed 1 million suns. galactic collision is thought to spawn supermassive black holes. Like celestial dancers, two galaxies merge. A supermassive black hole is formed when the galactic cores unite. This is Centaurus A, the marriage of two galaxies, a white one shaped like a basketball, and the dark one that we see edge on. At their single heart is a supermassive black hole. It has 1,000 times the mass of that hole in the Milky Way. And here's another, just as big. A supermassive black hole is surrounded by an accretion disk. Subject to irresistible gravity, matter swirls inward. Some matter jets at right angles to the disk, saved at the brink by the shock wave around the central vortex. Every hour, the equivalent of 4 Earths is consumed. This is an even bigger supermassive, a hole with the mass of 2.5 billion suns. It's at the center of the galaxy Virgo A. A great plume of material ejects across space. Here is Virgo A from the Hubble Space Telescope, the jet plainly visible. And this from a telescope on Earth. But the most incredible black holes are linked to quasars. Quasars burn at the center of remote galaxies, so fierce and bright that they outshine the galaxies themselves. Quasars are fueled by the hungriest black holes, supermassives that consume the equivalent of 600 Earths an hour. These are Hubble pictures. Quasars are among the most luminous and powerful objects in the universe. Albert Einstein, the great 20th century physicist, predicted many of the effects of supermassive objects. His general theory of relativity explains how bodies not only bend light, but distort the space around them. Our universe ripples with the push and pull of gravity, the exertions of supermassive objects. A black hole is the ultimate distorter. It so bends space and light that we've no idea what happens inside. It could be a wormhole, a gateway to other parts of the cosmos, perhaps even to another universe. Future Shuttle. It takes off as a plane and it climbs. With sufficient height and the right speed, the pilot engages the rocket engine. Future Shuttle is in space. Airport to orbit in one smooth hop. At the leisure wheel in the sky, it's Friday night. Future Shuttle is bang on time. Less than half an hour from takeoff, another party docks and checks in for a weekend in space. A break to watch the heavens above and the earth below. But this wheel is much more than a resort. It's a spaceport, a staging post for onward journeys to the moon. For the moon is colonized, and for economy's sake, it's more efficient to ferry cargo and personnel from Earth orbit than directly from Earth. In gravity 1/6 of ours, the transporter pod coasts to touchdown. This is no campsite. It's a metropolis. People work and live here. Scientists, miners, gardeners. And beyond, on Mars, more colonies. Sealed, self-contained cities, modelled on the lunar bases and serviced by them. The Moon and those spaceports are our stepping stones to the planets. That's the fantasy. This is the reality. ISS, the International Space Station. Assembled in Earth orbit around a Russian core, components are from America, Canada, Europe and Japan. Completion is scheduled for 2004. Shared by 13 nations, there are multinational crews and robots like this, an inspection ball. It monitors astronauts on spacewalks and checks the superstructure. Robot arms reposition modules. Every technology to maintain a structure the size of a football field. Initially, crews travel aloft on the old space shuttle. Their lifeboat, Soyuz, the ferry used by the Russian space station Mir. 6 to a crew, lots of room, with tours of duty just 90 days. Life on ISS is congenial, luxury compared with Mir. ISS is costing $100 billion. It takes over where Mir leaves off. The main objective? To test the long-term effects of living in space, vital if we're to get to Mars. And this is the new shuttle. Or at least a half-size prototype, the X-33. As construction of the International Space Station begins, so do test flights of the X-33. It's the forerunner of VentureStar, the shuttle that'll lift cargo 20 tons at a time to ISS. And it'll do it 10 times more cheaply than the old shuttle. And unlike the old shuttle, which dumped fuel tank and boosters on every flight, VentureStar is all-in-one, entirely reusable. From Earth orbit, a rocket to Mars. It's the late 21st century. Thanks to spaceports like ISS, the red planet is now colonized. The rocket jettisoned, we approach this cold little world and its wispy atmosphere. Millions of kilometers from home, a city of human beings. But it's life in a bubble. Airtight corridors connect labs, factories, offices, homes. Outside with no spacesuit, you're finished. This city is self-sustaining. Biospheres produce food. Energy is solar-powered. Everything is recycled. Rocket packs are fun. but to be free of pressure suits. Couldn't we turn Mars into Earth? Possibly, but it would take 100,000 years to induce a greenhouse effect and breathable air. To travel beyond Mars from the spaceport of the future, it would take up to 15 years to reach Pluto, the outermost planet. We're held back by our propulsion systems and limited fuel capacity. Solar energy can help, but on a voyage through the outer planets, it's a diminishing resource. The further we journey, the dimmer is the light of the sun. But there's still the solar wind. We might gather it in vast sails and drift outward on electrified particles blown from the sun. Beyond the solar system, we need new propellants. Even at 1/10 the speed of light, it would take us 40 years to reach the nearest star. Ion or nuclear propulsion might give us the thrust, but for the time being, such voyages are science fiction. So, where next? The Moon and Mars are first on our list. But what about Venus, Earth's hot sister? Might we colonize this hellish planet, disperse its clouds, reverse the runaway greenhouse effect? Perhaps. The trick could be to seed the atmosphere with green algae. It feeds on the crushing carbon dioxide and releases oxygen. Water accumulates on the surface. The steamy climate cools. Life takes hold. It's no quick fix. Only after hundreds of thousands of years does Venus start to look like Earth. And even if it's possible, is such planetary engineering desirable? Nature has a habit of reasserting itself. But how about this for planetary engineering? It's the idea of space guru Arthur C. Clarke. A tower rises 36,000 kilometers from the surface of the Earth. An elevator to orbit. The tower is one of 4 reaching from the equator, the spokes of a gigantic wheel of which Earth is the hub. A carousel to the cosmos. If you have any comments on the content of this program, we'd be pleased to hear from you. Write to us at this address or send an email.